Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at amount of substance, and in particular we're going to be looking at solution calculations and titrations. So by the end of today's lesson you should be able to do the following. We should be able to recall the mole equation for solutions, use C1V1 equals C2V2 to calculate dilutions. We should be able to apply the mole equation for solutions to calculate unknown volumes and concentrations. And finally, we should be able to apply the mole equation for solutions to back titrations. So first up, let's look at the mole and solutions and the equations that are associated with it. Here we go. The first thing is concentration. Concentration simply tells us how much stuff is dissolved in a given amount of water. So we might have a substance which is dissolved in the solution, and if we divide the amount by the volume, then we end up with a concentration. In chemistry we normally discuss things as moles, so our concentration here is equal to the number of moles divided by the volume. Our given volume, our standard volume here is a litre or a decimeter cubed, so our concentration will have units of moles per decimeter cubed, and we can either write that /dm cubed, or we can have moles dm minus 3. So concentration can either be in moles per volume, or equally, if we got a solid, we can work out the mass over the volume. So we might have the mass divided by the volume, and in which case we would have units here of grams per decimeter cubed, or grams dm minus 3, which is equally known as a density value. Now then, normally we are working in moles, and we might be asked to find out how many moles there are in a given volume and a given concentration. Our usual units for volume are centimeter cubed, which is equivalent to a milliliter. So we might say 10 milliliters or 10 centimeters cubed. Our concentration, as we just said before, have the units of moles per decimeter cubed, and also sometimes this is called the molarity, which is a capital M for molarity of a solution. And the final thing, of course, is the moles, which has got the units simply the mole. So when we're calculating either our concentration, our volume, or our moles, we sometimes have to consider a conversion between centimeters cubed to decimeters cubed. Our conversion from centimeters cubed to decimeters cubed is important. So 1 centimeter cubed is equivalent to or equal to 1 times 10 to the minus 3 decimeters cubed. The other way round is 1 decimeter cubed is equal to 1 times 10 to the 3 centimeters cubed. So often our equation for the moles, when we come to our overall equation, is the moles we describe as the volume, which we give in centimeters cubed, times by the concentration, which has units, as we've just said, of mole dm minus 3 divided by 1000. Now the factor of 1000 here comes from the fact that we convert centimeters cubed to decimeters cubed to keep everything consistent. This is sometimes simplified here to moles is equal to concentration times by the volume divided by 1000. C times V over 1000. You need to be able to rearrange that for concentration, for volume, and for moles in order to be able to work in this unit. Okay, so now we've looked at our equation that we've just seen before. We'll write it down here again next to our dilution. Moles is equal to C times V over 1000. Let's see what happens if we use it to work out a concentration, and also see if we can use it to work out some unknown concentrations, perhaps when we do a dilution. So let's imagine we've got a beaker here, and we've got a certain number of moles of substance. There we go, we just draw them in like that. And let's imagine that this is 10 centimeters cubed. So I'm going to say I've got 0.5 moles of the substance in 10 centimeters cubed. We quickly do the equations. So our concentration is equal to 1000 multiplied by the number of moles divided by the volume here. So we now have 1000 times by 0.5 divided by 10, giving us a total concentration of 50 moles per decimeter cubed. Now let's suppose that that really is a very high concentration. Let's suppose that we're now going to put all of this solution into a new beaker over here. We're not going to change the number of moles, but we're going to increase the volume of water to 1000 centimeters cubed in total. So we're adding to that, in fact, 990 centimeters cubed. The number of moles is the same. The question here is, what is our new concentration? And how can we do that nice and quickly? So I'll give you a second just to think about that, and then I'll show you a nice little trick we can do. So, how did you get on? Alright, I'll show you. Let's have a look. Here we're going to call this one beaker number 1. And we'll call this one beaker number 2. Now, what we can say about the moles in number 1 is going to be equal to the concentration times by, times by the volume. Now then, in beaker number 2, we also know that because we're not changing the number of moles, that the number of moles in beaker 2 is going to be the same as in beaker 1. and therefore the number of moles in 1 is going to be equal to the concentration in 2 multiplied by the volume in 2. Each of these cases we've got 1,000 underneath again. And what this means is if we bring these two equations together, cancelling out for moles 1, we end up with an equation that looks like C1 V1 over 1,000 is equal to C2 V2 over 1,000, and we can simply cancel out then both of our factors of 1,000, and we end up with a simplified equation here which says the concentration in 1 times by the volume in 1 is equal to the concentration in 2 times by the volume in 2. And this will help us calculate some simple dilutions. We can apply it to our situation here. So finally, if we want to work out this unknown concentration, well, our concentration in 1 we knew, our volume in 1 we knew the volume in 2, so our concentration in number 2 is simply equal to the concentration in 1 times by the volume in 1 divided by the volume in 2. If we put those numbers in, we have 50 times by 10 divided by 1,000, giving us a new concentration of 0.5 mole per decimeter cubed. Okay, so back to our simple equation for concentration and dilutions. Here we are, C1 V1 equals C2 V2. Now we're going to go and move on to look at how we can actually work out some titration calculations using our volume concentration over 1,000. So let's see if we can use our knowledge here of our solution calculations to work some unknowns out from a titration. Here's our first example. We'll have a look at a couple of these. Here we got, it says 25 cm cubed of 0.020 moles per decimeter cubed of sulfuric acid neutralizes 18.6 cm cubed of sodium hydroxide solution. And then we've got a balanced equation here where it says H2 So4 AQ plus 2NaOH AQ goes to Na2 So4 solid plus 2H2O liquid. And the question here is find the concentration of the sodium hydroxide solution in moles per decimeter cubed. So first of all, let's just identify in our equation here what we know. We know that we got 25 centimeters cubed, which is a volume, of course, and we got 0.0 moles per decimeter cubed, which is a concentration. We know that's of the sulfuric acid. So we got quite a lot of knowns about the H2SO4. And the other thing that we know about here is we got 18.6 centimeters cubed of sodium hydroxide solution. Here we got sodium hydroxide, and just to note, we've got a 2:1 ratio sodium hydroxide to H2SO4. So let's go right ahead and see how we do the equation. Perhaps you might want to have a quick go, pause the video here and have a go yourself. But what we're going to do is we're going to work out something about the known, which is the moles of H2SO4. We know two things about the H2SO4, and that's going to be equal to the volume times the concentration over 1,000, and in this instance we've got a concentration of 25, we've got a concentration of 0.020 over 1,000, which is going to give us a value in moles. If we put that in our calculator, we'll get an answer here of 5 times 10 to the minus 4 mole. So there's our known value. If you want to know the moles of sodium hydroxide, well, we look at our equation. We got 1 mole of H2 So4. It's going to make 2 moles of sodium hydroxide, so our mole ratio is 2 to 1. So the moles of sodium hydroxide is what we want to know over what we do know. So 2 divided by 1 times by 5 times 10 to the minus 4 is equal to 1 times 10 to the minus 3 mole of sodium hydroxide. Then we were asked to find the concentration of the sodium hydroxide solution. So we now have both a moles and also a volume. So our concentration of sodium hydroxide here is equal to the moles times by 1000 divided by the volume, which is going to be 1 times 10 to the minus 3 times by 1000, all divided by a total of 18.6. And if we plug that into our calculators, we end up with a value of 0.0538 moles per decimeter cubed. Now, this question would have worked exactly the same, perhaps if they'd given us a concentration instead of a volume here. Well, would have done the moles of sulfuric acid the same, worked out the moles of sodium hydroxide, but instead of using concentration, would have used the volume is equal to moles times 1000 over the concentration. So just using a different equation. The next thing that we might be asked here is the following. So can we find the concentration of the sodium hydroxide solution here in grams per decimeter cube? So our conversion of moles per decimeter cubed to grams per decimeter cubed, we're simply going to be multiplied by the molecular mass of the solid. So in this case, with sodium hydroxide, the molecular mass here is equal to 23 for sodium plus 16 for hydrogen, 16 for oxygen plus 1 for hydrogen, giving us 40 grams per mole. So to convert our concentration from moles per decimeter cubed here to grams per decimeter cubed, we simply multiply our concentration by the MR of sodium hydroxide. There we go, and you should end up with an answer of 2.15 grams. Brilliant. Well done if you did that all by yourself. So we're going to move on now to the slightly more abstract idea here of back titration. So a back titration is done to analyse a base or acid that does not react easily or quickly with an acid. Instead, the base or acid is treated with an excess, so that's too much, of acid, and then the leftover acid is titrated. Using this idea, you can then work back to find out about the original base. Now, to try and explain that a little bit easier, I'll give you an example. So let's first imagine that we had to find out a certain amount of moles of some calcium carbonate. So we've got our calcium carbonate here in our beaker. Now, let's pretend we've got X moles, in other words, an unknown amount of calcium carbonate. To this, we're going to pour in a solution of hydrochloric acid. And we're going to know how much of this we're going to add. We're going to add 10 moles in total, and we're going to add this to excess. So we're going to add the total 10 moles and it will be in excess. We'll know it'll be in excess. How do you know? Well, that's right. At some point in the future, it's in excess. We've added our 10 moles of hydrochloric acid and all of our calcium carbonate is now disappeared. So our hydrochloric acid is reacted, and it's reacted with the calcium carbonate to make water, carbon dioxide, and calcium chloride, which is otherwise aqueous. Of course, we just have to balance that up. Now, because the hydrochloric acid was in excess, it's now possible to do a titration with that hydrochloric acid to find out how much is reacted. So if we titrate the hydrochloric acid with, classically, let's just go for sodium hydroxide, we find out perhaps that in this reaction we've got 4 moles of hydrochloric acid left over. We've done the titration with sodium hydroxide. There's 4 moles of hydrochloric acid left over. What that means is that of our original 10 moles of hydrochloric acid, there are 4 moles left over, and therefore 6 moles must have reacted with our calcium carbonate. Six moles of HCl reacted with the calcium carbonate. And because if we look up here, we've got a 2-to-1 ratio. If we had 6 moles of HCl, that must mean we have 3 moles, because of the 2-to-1 ratio, of calcium carbonate. And there is our example of our back titration. I'll give you a full example in just a minute. So here's another example. Let's see how we get on. It says aspirin is a monoprotic acid. That means it's got 1 hydrogen for each acid molecule. That can be analysed by a back titration with sodium hydroxide. So we've got a monoprotic acid. And that's going to react with the sodium hydroxide. And because the sodium hydroxide has got 1 OH, that means that we're going to importantly have a 1-to-1 ratio here in our neutralization reaction. So we get a salt plus water. And it says then we add 0.25 moles of sodium hydroxide here, which is an excess, i.e. too much, to Y moles of aspirin, and make the resulting solution into here 250 centimeters cubed of stock solution. It then says we titrate 25 centimeter cubes portions of the solution which require 0.01 moles of HCl for neutralization. So here we got the leftover sodium hydroxide reacts with hydrochloric acid in a 1-to-1 ratio. It says here the solution requires 0.01 moles of hydrochloric acid for neutralization. we've got a 1:1 ratio, so we must have 0.01 moles of sodium hydroxide that reacted. Now importantly, we only titrated 25 centimeters cubed, but our initial stock solution, we said here, was 250 centimeters cubed. So 0.01 moles in 25 cm cubed, well, that must mean we had 0.1 moles, so 10 times more, in 250 centimeters cubed of solution. We had 0.1 moles left over from reaction with a monoprotic acid. That means the moles of sodium hydroxide that reacted with the aspirin is going to be equal to 0.25 moles, which we get from our excess up here. Take away 0.1 moles, which is the amount that reacted, means that we have 0.15 moles of sodium hydroxide that reacted with a monoprotic acid. Because the monoprotic acid to the sodium hydroxide was a 1:1 ratio, we must have had 0.15 moles of aspirin to start with, the monoprotic acid. And there we go. That concludes our lesson there on back titration and the lesson on solution calculation. So just to recap again, you should be able to recall the mole equation for solutions, which is going to be moles is equal to volume times concentration over 1,000. You should be able to use C1V1 equals C2V2 to calculate dilutions. We've seen examples of applying the mole equation for solutions to calculate unknown volumes and concentrations. And finally, we've applied the mole equation for solutions to back titrations. We'll get plenty of practice of this in class, and I'll see you soon. Bye for now.